Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to help you understand how to interpret velocity graphs. So I'm going to talk about the directions here. Let's see, a 10 kilogram object moves along an x-axis according to the graph given. I'm referring to this graph right here. It's a velocity graph against time. Discuss the motion of the object assuming x at t equals 0 equals 0. So the idea is that this velocity graph is describing the motion of some object that starts at x equals 0 here. Now you'll notice at t equals 0, the velocity we can read off the graph is 5 meters per second. So this thing's already moving to the right at some sort of reasonable speed. During the next couple seconds, the velocities, notice how we're getting higher on this graph, the velocities are increasing up to 10 meters per second. Now I'm not going to do this in the example, but if we wanted to know where this thing was, that would be found by that area right there. All right. After 2 seconds, the velocity levels off and it stays constant at 10 meters per second. So this is a zero acceleration region. By the way, that would also mean there's no net force on this object. Going back here, we are accelerating. In fact, our delta v is 5 meters per second. Delta t is 2, so our acceleration is 2.5 meters per second squared in this region. So there would be a net force to the right on this object. Oh, let's see, what do we have here? 1, 2, 3, 4, 5. This is 6 seconds to 7, 8 to 9 seconds. Chat about that. So in this region, the velocity is increasing. This thing is accelerating in this region. See how the velocities are getting larger and larger and larger. And it's accelerating to the right because the slope is positive. If we were to calculate a delta v over delta t, we'd get a positive number. Since the acceleration is to the right, the net force also to the right. If we wanted to know where this particle is at this point, we would have to take that first area, add to it this rectangular area, and then add to it this trapezoidal area. Now, some viewers here may be asking, yeah, we could do triangle and a rectangle, and that's perfectly fine. That also would calculate where this object is. All right, so 9, 10, 11, 12. From 9 to 12 seconds, this region, it's a constant velocity. This thing is now moving at, looks like 16 meters per second to the right. Slope is 0, so our acceleration is 0. Also, net force is equal to 0 in this time frame. When we get to this time, if we want to know where that thing's at, we would add this rectangular area. Okay, so 9, 10, 11, 12. From 12 to 13 seconds now, you'll notice this thing gets stopped fairly abruptly. All right, this point right here is looking like 9, 10, 11, 12 seconds. 16 meters per second, so it's moving reasonably fast. This point right here, though, is 13 seconds, 0 meters per second. So when you calculate a delta v, that's a fairly large delta v, and that's going to be negative 16 meters per second. And if you divide by the delta t, which is just 1 second, we get an acceleration of minus 16 meters per second squared during this time interval. Net force is to the left because the acceleration is to the left. And the net force can be calculated easily because we know the mass, but this was just meant to be kind of a conceptual video on how to interpret these velocity graphs. So let me go back and kind of overview some things that I think are important. In this graph, these velocities are all positive. There's nowhere, including the end, even when we're in this region, all those velocities are still positive. So this object moves to the right the entire time frame, out to at least this time frame, this time right here. Regions where there are accelerations are here, here, and here. Now you can tell when something's accelerating because its velocity is changing. Right? Remember, accelerations change in velocity over change in time. So you can't have any acceleration without this. So these are the regions in red where the velocities are changing. The first two have positive accelerations and therefore forces that point to the right. This last one has a negative acceleration and therefore the net force on the objects to the left. So those are some important things I think about reading graphs and how to kind of link it with forces. And I hope that this has helped. Have a great day.